Alright class, this video is going to cover section 8.2, which is all about estimating population means. So, how do we estimate the population mean when we only have a single sample? We do not expect the sample mean to be equal to the population mean because there's likely to be some sampling error. So in order to make an inference about the population mean, we need some way to describe how well we expect our population mean to be represented by the sample mean. The most common method for doing this is the way of confidence intervals. So we're going to be constructing 95% confidence intervals. A 95% confidence interval means that 95% of all sample means, so we're still looking at distribution of sample means, lie within 1.96 standard deviations of the population mean, and the sample is normal. Our confidence interval is the range of values likely to contain our true population mean, mu. So how do I calculate the 95% confidence interval? Okay, we're going to use our sample mean as an estimate of our population mean, and we're going to have to calculate how big our margin of error is. Okay, so the bigger our population gets, because we're taking the square root of that, the smaller our error will become. So the equation is our error is 1.96, which is the number of standard deviations away from the mean to be in the middle 95% of data, times our sample standard deviation over the square root of n, where n is the size of our population. Now, this 1.96, that's for the 95% confidence interval. If we want to construct a 90% confidence interval, that is going to be found by replacing 1.96 with 1.645, because that's how many standard deviations you would need to be away from the mean in order to have the middle 99% of data. And for a 99% confidence interval, we would replace that with 2.575, because that's how many standard deviations away from the mean you would be to the left and right in order to be the middle 99% of data. But we're going to focus on calculating 95% confidence intervals. So a confidence interval for a population mean always has our sample mean at the center, so that's x bar, and our error is how far away we are to the left and our right of our mean. It's going to make our interval. So I calculate my confidence interval by taking our sample mean minus our error to our sample mean plus our error. So let's consider the daily protein intake for a sample of 267 men with a sample mean of 77 grams and a sample standard deviation of 58.6 grams. So I need to go ahead and I want to find the margin of error for a 95% confidence level and construct my confidence interval. So I know that error is 1.96 times s, which is our sample standard deviation, over the square root of n. So that gives me 1.96 times 58.6 grams, that's our standard deviation, over the square root of 267. That's going to give me an error of 7.03. So in order to construct this confidence interval, okay, I'm going to take x bar minus our error to x bar plus our error. That gives me x bar, which is 77, minus, why don't we go ahead and round this to 7, and x bar plus 7. So 77 plus 7. That gives me a confidence interval of 70 to 84. So I'm 95% confident that I'm confident that 95% of the sample means would fall within this range if I was to take these samples over and over and over. So how does this confidence interval compare to the recommended daily protein take of men? And that interval is supposed to be 55 to 60 grams. How does this compare? Well, you could say that it's a much wider interval. You could also say our values are much higher than the recommended dose of daily protein intake for men. Next, let's look at the recommended daily protein intake for women. So we have a random sample. This time our sample has a size of 264, and our mean is 59.6 grams. So we find from our sample the average consumption of protein by women is 59.6 grams with a standard deviation of 30.5 grams. So I want to estimate the population mean and give a 95% confidence interval. So we're going to estimate our population mean is 59.6 grams, and I need to construct a 95% confidence interval. So the first thing I have to do is calculate my error. So our error is going to be 1.96 times our sample standard deviation, which is 30.5, divided by the square root of our sample size, n, which is 264. That's going to give me 3.68. So my confidence interval is going to be my sample mean minus our error to our sample mean plus our error. And I would find a confidence interval of 55.92, so let's say 5.92 to 63.28. How do these values compare to the recommended daily allowance of 45 to 50 grams? First off, there's a wider difference in these two values, right? There's 5 grams difference and there's 8 grams difference. So there's a wider range of values. It's also higher than the highest recommended dosage, but not as high as it was for the males in the previous slide. So it's important for us to think about what these confidence intervals, once we construct them, what they truly mean. Now let's say I want to know what size error I can expect, right? We would want our error to be as small as possible, right? And the smaller our error is, the bigger population we would need. So we have to make sure we have kind of a balance so that we aren't sampling, say, hundreds of thousands of people, but also so that our error isn't incredibly huge. So if we need to estimate our sample size, we would take our sample size n to be 1.96 times our standard deviation divided by our error squared. And we get this from the equation for how we calculate the error, but you don't need to know how to solve that problem. So just know that this is the formula you will be given on an exam, and you will have to know how to use both of these. So let's go ahead and calculate a sample size. So let's say I want to study housing costs in a rural county by sampling recent house sales. And my goal is to find a 95% confidence interval of the housing costs. Previous studies suggest the population standard deviation is about 7,200. What sample size, at a minimum, should be used to ensure the sample mean is within 500 of the true population mean? This is my error. this is my standard deviation, and using this information, I can calculate my population size. I have n equals 1.96 times S over our error, and it's really important to do this part, squared. So I find that n equals 1.96 times 7,200, let's make that look like a 9, divided by our error of 500, all squared. So I would get a sample size of 796.6. Now, we need to remember to round up. N is always going to be a whole number, no decimals involved. I can't survey 796 houses, so I'm going to round this up to 797. So we're going to need to look at a minimum of 797 recent house sales. Now, what if I wanted a smaller margin of error? Do we think that the sample size would go up or would it go down? Let's keep that in mind as we do this next example. So, what if I want to do this same study, but now I want to be within $100 of the true population mean? I want to get very, very precise. So, I take my sample size to be 1.96 times our standard deviation, which is still 7,200, divided by our desired error, which is now 100, squared. Well, as our error size is shrinking, we're dividing by a smaller number, so our sample size is going to get bigger. So as our error gets smaller, our lowercase n, gets larger. And that's really important to know that we would call these inversely related. If something goes down when the other goes up, or vice versa, that's an inverse relationship. So I'd plug this into my handy dandy calculator, and I would get 19,914.85. And you have to remember to round up, right? We don't have 0.85 of a house. So I have 19915 as our final answer.